Hi, thank you very much. It's a pleasure to be here, and today I'll be talking about trapped ion quantum computing at Honeywell. I know many people have been surprised to hear that Honeywell is building quantum computers, but actually for a long time, Honeywell had a lot of component technologies in different parts of the company, uh, and like vacuum and cryo and optics, lasers. And for the past decade, there's been an effort to develop quantum computing, starting with making ion traps in our microfabrication facilities, and also applying Honeywell's control expertise towards controlling quantum systems. And today, we have a sizable team of scientists and engineers focused on quantum computing, with a couple of commercial systems available for customer use, and many more development systems that we use in-house for research. And so the work I present here in this talk is the combined efforts of the entire team. And so why did we choose trapped ions as our qubit? Because our goal is to make the highest performing quantum computers. And if you consider the DiVincenzo criteria for a quantum computer, trapped ion qubits have excellent fidelity for quantum gates, for initialization and measurement. And they also have the longest coherence times compared to other qubit technologies. So we can get all-to-all connectivity and features like mid-circuit measurement and conditional logic with the trapped ion quantum computing schemes. And so the concepts for trapped ion quantum computers have been around for more than 2 decades now. And here's a paper from Dave Wineland's group from NIST dating back to 1998, outlining everything they knew about trapped ion quantum computing back then. And this figure here on the right showed an architecture where ions are moved around in this device to different zones for storage and for logic operations. And so this picture solved one of the big concerns at the time regarding the scalability of having all the ions in one long chain, where you have more and more vibrational modes to control as you add more qubits. And managing all those vibrational modes poses a real challenge. Now, this idea of moving ions around was popularized by this Nature paper in 2002, where the term quantum CCD, the quantum charge coupled device, was coined. And so this allows us to have short ion chains and prevent the complexity of the system from blowing up. So over the years, many groups have worked on different aspects of QCCD architecture, and from trap design to transport moves to robust gate schemes. But nobody has put everything together. It's a fully operational QCCD quantum computer until this last year, when our team launched our first commercial trapped ion quantum computer. So this is our ion trap that we put in our commercial systems. And you can see there are 2 RF rails, or electrodes, shown in green here. And we have 3 rows of segmented electrodes where we can apply varying voltages to move the ions around. The interaction zones are color-coded in blue, and the additional zones for storage are in between the interaction zones and on the ends as well. At this one end of the trap, we have a load hole where neutral atoms can come through from the backside of the chip, and we can generate ions here by photoionizing them, the neutral atoms, and trap them once they're ionized. We use hyperfine clock states of ytterbium-171 as our qubit. And because we can't directly laser cool these ions once we store quantum information in them, we added a new species, barium-138, and this is purely for sympathetic cooling during circuit execution. We use a Mulmer-Sorensen scheme for our 2-qubit entangling gate by applying a spin-dependent force on the ions, coupling off resonantly to the vibrational sidebands to acquire geometric phases. These gates can be applied simultaneously in every interaction zone. So this trap can hold short ion chains in every zone, And by maneuvering them in and out of these zones, we can maintain high fidelity quantum operations and individual addressing with negligible crosstalk. So here's a picture of our ion trap, and I have an animation to show you how it works. So here we have, we load the ion trap by photoionizing neutral atoms coming through the hole from the backside of the chip. And then we trap them once they're ionized. And once we have the ions, we can transport them to an interacting zone where we can initialize or measure or perform single qubit gate operations on the qubit by turning on the corresponding lasers. For 2 qubit gates, we have to first combine the ions from 2 different wells and turn on the 2 qubit gate lasers to perform the entangling operation. And afterwards, we separate them and move them to their next location. To show you how this works in the quantum algorithm, let's take this example algorithm here. We mark the qubits in red and green and blue, so we can track them. We start with initializing them all to 0 by optically pumping them with a laser. And then at t equals 1, we want to perform Hadamard gates on the red and green qubits. And so we shine lasers on them. And here they're conveniently already in the gate zone. At t equals 2, we want to perform a CNOT on the red and green qubits. So we have to first move them together. And then we turn on the 2 qubit gate lasers to perform the operation. And then at t equals 3, we need to perform a CNOT gate between red and blue. So we have to swap this red and green qubits first, and then move the red and blue together. And then we can turn on the 2 qubit gate lasers on the right zone on the right to perform the operation. And finally, here we want to measure the green qubit. So we turn on the measurement laser, and we can do this without disturbing the qubits in the other zones. And based on the outcome of that measurement, we can perform conditional quantum operations on the other ions. And we can also reinitialize the green qubit and put it back into the circuit as a new qubit. So here are some videos of ions performing some of the transport moves. On the top, you can see the 2 ions that came together from distant wells. And then when they're combined in the same well, they actually just show up as a one bright dot there because the camera can't resolve it. And on the bottom, you can see those 2 ions reordering themselves and changing positions from left and right. So currently, we have 2 quantum computers available for customers to use, creatively named H0 and H1. H0 was the first system we launched in the spring of 2020 with 6 qubits. And H1 was launched in October last year and is currently operating with 10 qubits, but it has the capacity to hold a lot more. The coherence time clocks in a few seconds for both systems. And H1 has better measurement and gate fidelities than H0. Both of them have all-to-all connectivity and mid-circuit measurements and conditional logic just by the nature of this QCCD design. And we offer high-resolution single qubit rotations as native gates. We usually run quantum volume circuits to benchmark our systems. And the quantum volume 64 on H0 is purely limited by the number of qubits. And we recently demonstrated a quantum volume of 512 on H1, which is the largest quantum volume ever measured on a quantum computer that has been reported. So this quantum volume metric was first proposed by the team at IBM in an attempt to move beyond just qubit count into something that more accurately describes the performance of a NISQ quantum computer. And for a quantum volume 2 to the n, you have to generate these random circuits for n qubits with depth n. And for each step 1 circuit, you perform a random SU4 for each pair of qubits, and then you randomly permute all your qubit order. And then you select a different set of random SU4s and a different permutation for each round. And you do this for n rounds. And then at the end, you measure the qubits and look at the distribution there. So any random SU4 can be decomposed into 3 2-qubit gates with single qubit rotations in between. And if you understand your error rate, you can approximate this SU4 with fewer 2-qubit gates. And so we take the distribution of the measurement outcomes from these random circuits and compare them to the expected distribution from classical simulation. If there are no, and we look at these heavy percent in the heavy outcome. If there are no error in the quantum computer, the percent should average out to about 85%. To pass this quantum volume benchmark, and the system has to pass the threshold at 2/3, according to the protocol. So for the 512 benchmark, we performed 300 different random circuits with 20 shots each, and the data is plotted here. And you can see our average heavy outcome is averaging at 73%. And then with enough statistics, the error bars also clear that 2/3 bar. So this 512 is 2 to the 9th, so 9 effective qubits. And these random circuits average about 77 2-qubit gates per circuit. So it's actually pretty challenging. And from our calibration data, you can see the gate fidelities and measurement fidelities are quite good. And these are typical performance specs on H1, and we try to maintain the system to a minimum of 99.5% fidelity for customer use. On the right, you can see our quantum volume trajectory over the past year from 16 back in the beginning of 2020 to 512 that we demonstrated just last month. And we expected that this trend to continue as we increase the number of qubits and further improve the fidelities. If you're one of our users, you don't have to worry about any of the quantum CCD operations. You can just submit your program in OpenQASM through a cloud portal, and the compiler will automatically translate that into a schedule of transport and gate operations. And these lower level instructions are then sent to our control system, and the control system will fire off signals to different parts of the hardware in a synchronous manner to perform the prescribed circuit. The measurements results are then returned to the user via the cloud portal. Many companies have already run algorithms on their quantum computers with an eye towards practical applications. Many of them partner with software companies and academic research groups on these projects. You may recognize some of these names. So, for example, DHL and Cambridge Quantum Computing ran a BQIT type algorithm for optimally packing boxes of varying weights and sizes into containers, basically a knapsack problem. And they were able to find the optimal solution with a small number of boxes. The Samsung Imperial College in London did a simulation of the dynamics of an interacting spin model where they were able to run very deep circuits with as many as 100 2-qubit gates on our system. The BMW and Tropical Labs was interested in optimizing supply chains, and they were using QAOA algorithms and show that it's as good as the classical heuristics, and they're looking forward to trying out new improvements that might outperform classical algorithms. And Merck and Zapata has also had some quantum machine learning algorithms for supply chain optimization. So I wanted to show you some of the work we're doing on quantum error correction. This is work from Kieran Ryan Anderson and Natalie Brown on our team. We picked the color code because it fits within the 10 qubits we have on H1 right now, with 7 data qubits and 3 ancillas. And so we start by encoding a logical qubit, and then at the end, we measure the logical qubit. And in between, we perform repeated rounds of syndrome extraction, and we track the errors and perform the correction at the end, right before we measure the logical qubit. So many other groups have demonstrated logical qubit encoding and decoding, and even maybe one round of the syndrome extraction combined with some post-selection. But no one has been able to demonstrate this repeated cycles of syndrome extraction and real-time correction on the logical qubit before. And so the color code we're testing is a little different from the surface code in that it has a flag check in the first part of syndrome extraction. And if it's flagged, then it goes into the second round of syndrome extraction. Otherwise, we can just skip the second part. And so this is perfect for our conditional logic operations on our systems. So here's what the actual circuit looks like for the part 1 and part 2 of the syndrome extraction. And that's quite a few CNOT gates in each QEC cycle. Here are some of the preliminary results from H1. We went as far as 6 rounds of QEC cycles. And for that worst performing plus I state, the logical qubit was still performing quite well after 6 rounds, with 86% fidelity still after 323 CNOT gates. And from this plot, you can see the logical qubit picks up a couple % error for each round of QEC cycle, which is still better than no error correction, but worse than the physical qubit error rates. However, the logical qubit state preparation and measurement error comes out to average out to a 99.92%, which is actually better than our physical spam error at 99.77%. So that's very promising to see. And finally, this is our roadmap for the next decade of trapped ion quantum computing. We're here at H1 with 10 qubits, and we're working on increasing the number of qubits as well as the gate fidelity. And so we know we have room to grow there. And we've already microfabricated this H2 trap, which looks like a racetrack. And it's currently trapping ions, and we're able to transport them around the ring. So we're building up that system right now. For H3, we're looking at moving to 2D geometries. And here's a picture of a test chip with junctions. We've made this trap, and we are able to move ions through these junctions with fairly low heating. And looking forward, we will need integrated photonics integrated on the ion trap. And so here's one of the test chips we've built just for testing purposes. And so there's a lot of work to do between the NIST going to fault-tolerant quantum computing, and Honeywell will continue to make available to users these high-performance quantum computers as we develop them. And so if you're interested in using quantum computers or partnering with us, please contact us via email or from our website. And then there are additional publications from our group that I didn't have time to mention today. You can check them out if you're interested.